Please try this problem. Now let's discuss the problem. Here's a summary of the solution for part A of the problem. The concepts that are mentioned in the problem indicate that we should apply a Newton's second law problem-solving framework. The question asks for the minimum value of F sub applied to prevent the block from sliding down the wall. The problem uses this symbol, F sub applied, to stand for what the question is asking us for, and since the symbol is written without an arrow on top, it stands for the magnitude of the applied force. Although the question is asking about the minimum force to prevent the box from sliding down the wall, it's more useful to interpret that question as asking us for the magnitude of the borderline applied force, at which the block is on the borderline between sliding down the wall and not sliding. Since this is a minimum required to prevent the box from sliding down the wall, that tells us that if the applied force is greater than that minimum, the box definitely will not slide down the wall. On the other hand, if the applied force is less than the minimum that's required to prevent the box from sliding down the wall, then the box will slide down the wall. This also matches common sense, since it's the applied force that is preventing the box from sliding down the wall. It makes sense that a larger applied force would tend to result in the box not sliding down the wall, and a smaller applied force would allow the box to slide down the wall. To determine that borderline force, we need to assume that the magnitude of the applied force is at the borderline value. At the borderline value, should we say that the box will slide downward, or that the box will not slide? We need to notice that this is a certain type of problem. It's a minimum problem involving whether the object will slide. When you're working on a minimum or maximum problem involving whether the object will slide, the correct approach is to assume that at the borderline value, assume that the object does not slide. So I'll write down that that will be our assumption for this problem. We'll assume that at the borderline applied force, the box will not slide. Write down your assumptions for solving part A of the problem. On this problem, if the box is not sliding, that means that the box is motionless. So I'll indicate that by writing down that for part A of this problem, based on our assumptions, the velocity of the box is 0. Check the units. Yes, kilograms are SI units. Now we work on the free body diagram. Identify the object's weight. What is touching the box? The box is being touched by the surface of the wall, which exerts a normal force and a frictional force on the box. For part A, we're assuming that the box does not slide. So for part A, we apply static friction. And because for part A, we are assuming that the box is on the borderline of sliding, static friction will be maxed out. So we're applying maximum static friction for part A. And of course, we also know that there's this applied force from the box being pushed against the wall. The direction of the normal force exerted by a surface on an object should be perpendicular to and away from the surface that is touching the object. So, the direction of the normal force exerted by the surface of the wall on the box should point perpendicular to and away from the surface of the wall. So, the normal force for this problem points to the left, as I've shown here. We use this approach to find the direction of the maximum static friction force. In part A, the box is on the borderline of sliding down the wall. Therefore, to prevent the box from beginning to slide down the wall, the maximum static friction force points parallel to and up the wall. That is to say, the maximum static friction force for this problem points straight up. This is the first problem we've seen in this video series in which the normal force is horizontal and the frictional force is vertical. So let me ask you a question. Did you correctly determine the directions of the normal force and the maximum static friction force for this problem? If you did, excellent. And if you did not, well then remember that the normal force will always be perpendicular to the surface, and the friction force will always be parallel to the surface. And of course, we know what the direction of this applied force is because the direction of the applied force was drawn for us in the sketch that was provided with the problem. Now we work on the force table. We are not given a value for the magnitude of any of the forces. We do have special formulas that we can use to find or represent the magnitude of the weight force and the magnitude of the maximum static friction force. There are no special formulas for the normal force or for the applied force, so we represent the magnitudes of those forces by symbols. Of course, the magnitude of the applied force is what the question is asking us for. Before we break the forces into components, we must choose our axes. Usually we should choose an axis that points in the object's direction of motion. In part A, we're assuming that the box is not moving, but the box is on the borderline of sliding down the wall. And furthermore, looking ahead to part B, it turns out that in part B, the box actually will be sliding down the wall. So I will choose down as my positive y-axis for this problem. And I'll choose a x-axis that points to the right. Always write down your axes. We can use this rule to break the weight force, normal force, and maximum static friction force into components. For example, the weight force points down. We've chosen down as our positive y direction. So W sub y is positive. The normal force points left, which is our negative x direction. So n sub x is negative. N sub x has the same magnitude as the overall normal force, and the other component, the y component, is 0. The maximum static friction force points up, which is our negative y direction. So the y component of the friction force is negative. To break the applied force into components, we have to use the SOHCAHTOA process. Draw the legs of your right triangle parallel to your axes. We're using the horizontal and vertical axes for this problem, so our right triangle should have horizontal and vertical legs, and then the overall vector represents the hypotenuse. Because the overall vector is pointing up and to the right, our components point up and to the right. The x component of the applied force is pointing to the right, our positive x direction. So this x component is positive. The y component of the force is pointing up. Based on our axes, that's the negative y direction. So this y component is negative. The length of the hypotenuse represents the magnitude of the overall applied force. We don't know what the magnitude of the applied force is, but that won't prevent us from breaking the applied force into components. We've already indicated in the first row of our force table that we're using the symbol F sub applied, written without an arrow on top, to represent the unknown magnitude of the applied force. So, in our SOHCAHTOA equations, we represent the length of the hypotenuse with the symbol F sub applied. Then we use algebra to solve for the magnitudes of the components. The absolute value symbols remind us that it's our job to add the plus or minus signs in a separate step. We already determined that the x component is positive, and we already determined that the y component is negative, because the y component is pointing up, which we've chosen as our negative y direction. Now we can record our results for the x and y components of the applied force in our force table. Notice that we do not have a number for the magnitude of the applied force, but that didn't hinder us from breaking the applied force into components. We simply used this symbol, F sub applied, to represent the unknown magnitude of the applied force. And then we used this symbol in our SOHCAHTOA equations to represent the length of the hypotenuse. You don't need to have a number for the magnitude of a force in order to break that force into components. For this problem, we used sine to find the y component and cosine to find the x component. But for the previous problem, we used sine for the x component and cosine for the y component. The moral is that you shouldn't assume that you will use sine for x and cosine for y. Instead, use the SOHCAHTOA process we've illustrated here to determine the correct approach for each individual problem. Now let's work on our Newton's second law equations. For part A, we're assuming that the box does not slide, which means for this problem that the box is motionless. Since the box is completely motionless for part A, in both components, we can substitute 0 for both a sub x and for a sub y for our solution for part A. Now, which equation should we work with first? Well, at this point we notice that there are still two unknowns in the Newton's second law x equation, n and f sub applied. And there are also two unknowns in the Newton's second law y equation, n and f sub applied. Well, we would prefer it if there was an equation with only one unknown. At first it might seem like we're not ready to work with either of these equations yet, because they both still have two unknowns. So what should we do? Well, for this problem, we're going to have to apply a more advanced algebraic technique than the algebra that we were able to use for the previous videos. So to get started with that, we're going to have to consider these two equations simultaneously, considered together as a system of simultaneous equations, rather than thinking about the equations separately, one at a time. When we think about these two equations together as a system of simultaneous equations, we can see that we have a system of two equations. And in that system, there's a total of two unknowns. The only two unknowns in this system of equations are n and f sub applied. Well, when you have a system of two equations and two unknowns, that is a situation in which it oftentimes is possible to solve for the unknowns. There are a number of different approaches that you could take for solving this system of equations, but the most general approach for solving this type of system of equations is to use what's called the substitution method. Here's a summary of the steps for the substitution method for solving two equations in two unknowns. And as we go through this method, it should definitely seem quite familiar, because this is a method that you should have covered in your high school algebra courses. Step 1, begin by solving one of the equations for one of the unknowns. And you should try to solve for the variable that's the easiest to solve for. Well, if you compare this equation and this equation, I would say that the easiest variable to solve for is n in the Newton's second law x equation, because this is the only one of the variables that is not being multiplied by a number. So let's solve for this variable n. Rather than moving this term to the right, that would be fine, but it's somewhat better to move this term to the right, because that also allows us to get rid of this negative sign at the same time. Notice that we've solved for n, but in a sense we haven't completely solved for n, because we don't have enough information yet to get a single numerical value for n. Instead, the best that we were able to do for step 1 was to obtain an algebraic expression that represents n, 0.819 times f sub applied. Now, step 2, we should take this result for n and we should substitute it in for n in our other equation. That's why this is called the substitution method. So you can see now that I've taken this result for n and I've substituted it here into the Newton's second law y equation. Now, because of this substitution, now the Newton's second law y equation has only one unknown, f sub applied. So clearly we can now solve this equation for f sub applied, and that's our step 3. Step 3 is to now solve this equation for that second unknown. To simplify this expression, we combine like terms. Here's a simpler example of combining like terms to refresh your memory for how that process works. Now at this point we have to separate this term and this term. The best approach is to take this term and move it to the right side of the equation, because that allows us to get rid of this negative sign at the same time. And then it's easy to carry out the last step and obtain that f sub applied equals 65.2 newtons. So we carried out step 3 of the substitution method, solving this equation for the unknown. Now, if we want to, we can carry out step 4. That would involve taking our result for f applied and substituting it into this expression for n. That would allow us to calculate a value for n. Now, do we care what the value of n is? Well, the question was not asking us for n. The question was asking us for f applied, but I'm still going to go ahead and carry out step 4 and calculate a value for n, because that will help us to check whether our collection of results makes sense. When we complete step 4, we get the result that n equals 53.4 newtons. As usual, we have arranged our math for the Newton's second law equations in 2 adjacent columns. I think that this 2-column approach is especially helpful when you have to use the substitution method, because the 2 columns help us to keep the algebra organized. Now we're ready to answer the question. I'll round this result off to 65 newtons. In our solution, we interpreted the question as being about the borderline applied force at which the box is on the borderline between sliding down the wall and not sliding. But when I word my answer to the question, I go back to the original wording of the problem, and now I interpret the result as the minimum value of the applied force required to prevent the box from sliding down the wall. Now let's ask whether our results for part A make sense. This symbol and this symbol both stand for magnitudes. A magnitude can never be negative, so yes, it makes sense that both of these results are positive. Now notice that over here I've performed some extra calculations in order to determine values for the x and y components of the applied force and the magnitude of the maximum static friction force. These values will help us to check if our collection of results for part A makes sense. The magnitude of the normal force is 53.4 newtons, which equals the magnitude of F applied x. Does that make sense? Well, F applied x is trying to make the box begin moving to the right. In order to prevent the box from beginning to move to the right, the wall must exert a normal force that will cancel out F applied x. So yes, it does make sense that the magnitude of the normal force equals the magnitude of F applied x. So in this version of the free body diagram, I've drawn the arrow for the normal force the same length as the arrow for F applied x to reflect that relationship. Now let's ask whether our results for the y component make sense. The weight force is trying to make the box begin moving downward. But in our solution for part A, we assumed that the box would not begin to slide downward. So, F applied y and the maximum static friction force have to cooperate in order to cancel the weight force. So we expect that the magnitude of F applied y plus the magnitude of the maximum static friction force should equal the magnitude of the weight force. Well, 21.4 newtons plus 37.4 newtons does equal 58.8 newtons. So yes, our results for the forces for the y component do make sense. In this free body diagram, I've drawn the length of the arrow for the weight force equal to the sum of the lengths of the arrows for the maximum static friction force and F applied y in order to reflect this relationship. Now let's work on part B. Here's a summary of the solution for part B. I will choose to interpret the question for part B as asking for both the magnitude and the direction of the acceleration vector. The wording for part B says that in part B, the value of F applied will be reduced to half this value. Half of which value? Half of the value for F applied, which we determined in part A. In part A, we determined that the borderline value for F applied is 65.2 newtons. So for part B, the value of F applied will be half of 65.2 newtons, which is 32.6 newtons. You can see from this diagram that when we use F applied equals 32.6 newtons, the box will slide down the wall. Remember, 65.2 newtons was the minimum value required to prevent the box from sliding downwards. Make a note that for part B, the box will slide downwards. We draw a downward velocity vector to indicate the box's direction of motion after it begins moving for part B. As we work on part B, we have to carefully consider which parts of our solution to part A can be reused for part B, and which parts of the solution to part A no longer apply to part B. For example, we've now seen that the value of F applied that we discovered in part A does not apply in part B. Now let's work on the free body diagram for part B. We've decided that in part B, the box will be sliding. So, for part B, we apply kinetic friction, not maximum static friction. The kinetic friction force exerted by a surface on an object points parallel to the surface and opposite to the direction that the object is sliding. We've decided that in part B, the box will slide down the wall. So the direction of the kinetic friction force will be parallel to and up the wall. For part B, there's no need to make any other changes to the free body diagram that we used in part A. Now let's work on the force table for part B. For part B, the box is sliding, so we're applying kinetic friction, not maximum static friction for part B. So we use the special formula for the magnitude of kinetic friction. We've decided that for part B, the magnitude of F applied will be 32.6 newtons, half the value we determined in part A. In part A, we found that the magnitude of the normal force is 53.4 newtons. We don't assume that we can reuse that value in part B. Instead, we represent the magnitude of the normal force by the symbol N. We will use the Newton's second law equations for part B to determine the value of N for part B. In part A, we found these expressions for the components of the applied force. Now, the applied force has the same direction in part B as in part A. So, in part B, we can use these same expressions to calculate the components of the applied force. Here are those calculations. You can see that we find that in part B, F applied X is positive 26.7 newtons and F applied Y is negative 18.7 newtons. We record those results here in our force table for part B. Now let's work with the Newton's second law equations for part B. We've decided that for part B, the box is sliding down the wall. So the box is moving vertically in the Y component. The box is still motionless horizontally. The box is still motionless in the X component. So for part B, we can still substitute 0 for a sub x in our Newton's second law X equation. Unlike in part A, there's no reason to substitute a sub y equals 0 for part B. A sub y is what we need to determine in order to answer the question for part B, so we continue to use the symbol a sub y in our Newton's second law y equation. In the previous problems in this video series, we usually substituted 0 for a sub y and left a sub x as a symbol. This is the first case in this series for which we substituted 0 for a sub x and left a sub y as a symbol. When you tried part B on your own, did you see that you needed to substitute 0 for a sub x and leave a sub y as a symbol? The Newton's second law y equation now has two unknowns, n and a sub y, so we're not ready yet to solve this equation. The Newton's second law X equation has only one unknown, n. So we can solve the Newton's second law X equation for n. Here's our result for n. Remember that in part A, n equaled 53.4 newtons. But here in part B, we see that n equals 26.7 newtons. So if we tried to reuse the value for n from part A for part B, we would have gotten the wrong answer for part B. Now, we substitute our result for n into the Newton's second law y equation. The y equation now has only one unknown, a sub y, so now we're ready to solve the y equation for a sub y. Our result is that a sub y equals positive 5.57 meters per second squared. In the previous videos in this series, we usually began by solving the Newton's second law y equation for n, and then substituted our result for n into the Newton's second law X equation. This is the first video in this series in which we had to begin by solving the Newton's second law X equation for n, and then substitute our result for n into the y equation. Now we're ready to answer the question for part B. I interpret the question for part B as asking for the magnitude and direction of the overall acceleration vector. A sub x is 0, so the overall acceleration vector will have the same magnitude and direction as a sub y. Our result for a sub y is positive. The positive y direction is down, so the acceleration vector points down, as I've drawn here. A sub y has magnitude 5.57 meters per second squared, so the overall acceleration vector has that same magnitude, which I will round to 2 digits. Now let's ask, do our results for part B make sense? N is a magnitude, so it does make sense that our result for n is positive. In part B, n equals 26.7 newtons, which is the same magnitude as F applied x for part B. Does that make sense? Well, F applied x is trying to make the box begin moving to the right. To prevent that, the normal force has to cancel F applied x. So yes, it does make sense that these two forces have to be equal in magnitude. The applied force is half as big in part B as in part A, so it makes sense that our result for n is half as big in part B as it was in part A. Does it make sense that our result for A sub y is positive? Well, the box begins at rest, and in part B, the box then begins moving down the wall. In order for the box to begin moving down the wall, the acceleration vector must point down. Down is our positive y direction. So yes, it does make sense that our result for A sub y is positive. Does our result for the magnitude of A sub y make sense? On this problem, it's interesting to compare our result for the magnitude of A sub y to 9.8 meters per second squared. 9.8 meters per second squared is what the magnitude of the acceleration would be if it were caused by the weight force unimpeded by any other forces. But on this problem, the object's downward acceleration is impeded by friction as well as by F applied y. So on this problem, it does make sense that our result for the magnitude of A sub y is less than 9.8 meters per second squared. Now let's do a recap of our work on this problem. This is the first problem in this series that dealt with a vertical surface, the wall, rather than with a horizontal surface like a floor or a slanted surface, an inclined plane. Remember that for any type of surface, the normal force will be perpendicular to the surface, and the friction force will be parallel to the surface. For part A, we used the substitution method to solve a system of two equations in two unknowns. Here's a summary of the steps involved in the substitution method. Remember again that we saw that the substitution method was likely to be effective here because we had a system of two equations with a total of two unknowns. We had to break the applied force into components using this process. Some students might have difficulty applying SOHCAHTOA for this problem because we don't know a number for the magnitude of F sub applied, but we saw that that was not really an obstacle. We just used the symbol F sub applied, written without an arrow on top to represent the overall magnitude, and then we used that symbol, F sub applied, to represent the length of the hypotenuse in our SOHCAHTOA equations. We do not need to know a number for the magnitude of F sub applied before we can use SOHCAHTOA to help us represent the components. To solve a minimum or a maximum problem involving whether an object will slide, such as part A, assume that the object is on the borderline between sliding and not sliding. And for a minimum or maximum problem involving whether the object will slide, assume that at the borderline value, the object will not slide. Therefore, we apply static friction for part A. Since the box is on the verge of sliding, we apply maximum static friction. To prevent the box from sliding down the wall, the maximum static friction has to point up the wall. Since we're applying maximum static friction, we use this special formula for the magnitude of the maximum static friction to represent the magnitude of the maximum static friction in the first row of our force table. Since we assume that the box does not slide in part A, we can substitute 0 for both A sub x and A sub y in our Newton's second law equations. Compare part A for this problem with part A for the problem from the previous video. In this problem, the question asks for the minimum to prevent the box from sliding. In the problem from the previous video, the question asks for the minimum to make the block start moving. But although the two questions are worded differently, Both problems are solved using the same assumptions. Assume the applied force is at the borderline value, and assume that at the borderline value, the object will not slide. Read Part B carefully to see that we should set the magnitude for the applied force for Part B equal to half the value that we determined in Part A. As this diagram indicates, with an applied force that is less than the borderline applied force, we expect the box to slide down the wall. So for Part B, we applied kinetic friction, not maximum static friction. In Part B, the box is sliding down the wall, so the kinetic friction points up. For Part B, we used the special formula for the magnitude of kinetic friction in the first row of our force table. The direction of the applied force was the same in Part B as in Part A, so these expressions which we found for the components of the applied force in Part A were still applicable for Part B. So we used those expressions in Part B, together with the new 32.6 Newton magnitude for the applied force in Part B, to determine the numerical values for the components of the applied force in Part B. In Part B, we did not reuse the value for n that we obtained from Part A. Instead, we used the Newton's second law equations to determine a new value for n for Part B. In Part B, the box was still motionless in the x component. So in Part B, we could still substitute 0 for a sub x in our Newton's second law equation. And we had to leave a sub y as a symbol. This is the opposite of the pattern that we've usually seen for a sub x and a sub y in the previous videos. So in this video, we started by solving the Newton's second law x equation and substituted our result into the y equation, whereas in the previous videos, we usually started by solving the y equation and substituted the result into the x equation. Did you find this video to be helpful? If so, you can support the videos by making a monthly pledge at my Patreon page. You can visit my Patreon page by clicking the link on the screen or by using the link in the video description box. Thank you.